Okay, we're going to do a video on vectors in space. Now, for those doing specialist maths in stage 2, you've already have numerous experience of what we probably call vectors in a plane or vectors in 2 dimensions. A lot of these concepts are going to translate over very easily. So we're actually going to see if we can cover a number of concepts today. I've actually summarized all the information on this page below. But maybe we start understanding that, okay, space and plane and what we can do and what we can't do in terms of visually and algebraically solving problems. So in the opening problem, they talk about planes and they talk about space. And the idea, if we're a two-dimensional plane, we often talk about 2 coordinates x and y. In 3-dimensional space, we also add on the coordinate z. So the idea, okay, if you have a point P in space, it has 3 coordinates. In that case, 1 for x, 1 for y, 1 for z. Well, I've also put that over here. I've actually labeled that same point. And what I decided to do was I draw myself up. And if you've ever drawn a 3-dimensional object like a rectangular prism, you probably started by drawing 2 lines that were right angles or close to right angles, and 1 line that kind of came out, and giving the effect that maybe you're looking at this from a funny angle. So whilst we're drawing, all these lines have been drawn on a plane itself, the plane of this page. We're perceiving that this line is kind of coming out towards us, whereas these ones are flat on their own plane. And that's the way you can think about it. So if you look around your room, maybe just take a moment, look around. Okay, well, what could represent the ZY plane? Well, maybe a wall. And what about your XY plane, this plane in this space here? Well, that could be the floor. And what are you sitting on right now? Well, that could be a plane that's also parallel to XY, but a little bit elevated. So you can imagine a surface that's a little bit higher in terms of going up in the Z a little bit, but a fixed Z. Well, that would be the chair or a table top or something to that effect. And you can have ones, and they don't have to be parallel. They could actually be a plane that moves in all 3 X, Y, and Z. So, for example, I'm watching my OBS software on my laptop while I've got the presentation on my main screen, and my laptop is on a slant. So it's if I held it up completely vertical, it would be parallel to ZY, but it's actually slanting backwards into negative X space as well because it's on an angle. That's the way I'm looking at it, because my head is higher than my laptop screen, so I'm angling in that direction. So there's actually an infinite number of planes that you can draw in space, just like there's an infinite number of vectors you can draw in space, or infinite number of vectors you can actually draw in a plane. And we'll come to that later on. That actually, trying to put planes into space is one of the last things we'll actually do. But what we're going to do at this point is trying to get our head around what a coordinate looks like in 3-dimensional space. This is another concept we're going to come back to, because we're going to realize that this is actually quite difficult, particularly because we're trying to draw a 3-dimensional representation on a 2-dimensional surface being the plane on my page. So what I decided to do was I went in 3. I looked at my 3 coordinate directions and I decided, okay, well, I'll just travel 3 in the x direction, so that's 3i. You might remember some of these unit vectors. They're in single directions. 3i. All right, we're also going 3 in the y coordinate, so that's 3j. And what comes after j? Well, it's k. So we're going 2 units up in the k. All right. So we also remember in 2 dimensions that we can add vectors by drawing them. So if I was to take my k, I'm going to add the j. All right. So then that vector goes there. It looks like we're making something like a, okay, well, that's a, it looks like a rectangle, or it is a rectangle. All right. So then, but then we also have to add a k. The way we do that is I'm going to get this parallel with my x-axis. I can do that using this because you've got a bunch of parallel lines going across here. Probably need to just shift that a little bit. Okay, all right, roughly. I'll just move that. So 3 is 1.5. Okay, so I just drew a line that's basically I drew the same vector as 3i, and then I have my point of P actually sits out here, at least in terms of the way I drew the axis and I did the scale. And what you can, oftentimes you might see that she complete all the vectors. So you can add all the vectors together and you end up with something that looks like a rectangle, because that's what it is. I'm just going to do this freehand for the purposes of explaining that. All right. So then you have something like that. It's a little bit, okay. So that's where the point P is. So you've built a box to find where that coordinate point is. Now, is that helpful for you for other things? Not really. You can kind of visually have a look and see, okay, well, that's where point P is. It's a little bit up in the Z, is a little bit across in the X and across in the Y. Can you go and measure, like, for example, can I go and measure OP by doing that? Well, let's have a look. On my scale, that's about, maybe get some zeros to make it a bit easier. That's about 0.7, so double that is, oh, 0.8, double that 1.6. No, it's nowhere near it. In fact, I actually did the calculation over here for the distance from O to P, and it's 4.7. It's the square root of 22. We'll explain some of the formulas, and you're going to see they're actually very similar to the stuff that you did in two-dimensional vectors with just a extra dimension being the Z. And I'll come back to this diagram in a minute, kind of explain how that works in terms of doing that calculation. All right. So in terms of, okay, let's just go through a few of the concepts we've seen so far. And I'll summarize the things that you need to know in order to do 5a through to 5e. It seems like a lot of work, but these are very similar concepts. All right. Now, there's a couple of vector forms you may be familiar with. Now, there's another form in other textbooks where they use square brackets. So they basically write it like coordinates. So the coordinate P, 3, 3, 2 with the round parentheses. If you had a vector, like vector OP could be written as, so OP could be expressed as square bracket 3, 3, 2. I never see that in these textbooks. The old textbooks used to have them. I never see that anymore. So what they prefer now is something like this, where you write the numbers vertically. 3, 3, 2 with round parentheses. I think it has to do with it's kind of the vector notation, but I don't see why necessarily they have to use this. So the two kind of acceptable forms in this textbook is this or in component form. So component form, if I was to write it down in component form, is what I was actually drawing. 3i plus 3j plus 2k. Now, to describe what they are, if you look on the page here, all right, well, actually, these are just in 2 dimensions, but you remember them from there. So imagine instead of just 1, 0, it's 1, 0, 0, and j would be 0, 1, 0, and finally k would be 0, 0, 1. I think that is described later on. All right. There we are. Okay, yep, there we are. So OP can be represented XYZ is XI, YJ, ZK, where I is 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay. Well, we'll go through the rest of the different chapters, but I just want to summarize a few things. We'll see all of these as we go through. Okay, so just be familiar with the form. So either it's going to be like this, or it's going to be in this component form. The component form A can be expressed as A1i, A2j, A3k. I'm thinking with this A is represented by is 1, 2, 3 components, which are X, Y, and Z, and B in a similar fashion. Okay. Equality of vectors. A equals B. Now, this is not expressed in the book, but I wrote it out of habit. If with an extra F. That's not a typo. That's actually a mathematical term. It means if and only if. And so does this symbol here with the arrows pointing left and right. So if it's kind of going to the right only, it implies that. Or you can read it backwards and then say it's to the left. But if it has the arrow going in both directions, that means it's only true if it works both ways. So there are some statements like you'd say all vectors that are equal. They're not all collinear. Some are collinear. They'll have to share a point as well. If they didn't share a point, they would be parallel. But in this case, A1, I should probably finish that off actually. So what that means is A1 equals B1, A2 equals B2, and A3 equals B3. Okay, so all those components have to equal. All right. Now the other one looks very similar. Is the length of actually all of these are similar to be honest. The length of A, so which is to work that out, you take the components and square them and add them up. So we understood this came out of Pythagoras' theorem, and so does this, but it comes out of doing Pythagoras' theorem twice. If you kind of go back and you look at the way that you'd have to tackle something like my problem here, say for example, if I started here and I worked out the length from, maybe I'll call this point here Q. So that's the point Q would be 2 up in the Z and 3 across in the Y, and it lays on X equals 0. Well, you could go and find the length of that by just using Pythagoras, because we haven't moved in the X yet. Okay, and then you find this length. Then what you could, that's also the same as that length here if I drew it over here. And then what you could do then is you could also make a right angle triangle out of going across to P. And then you could work that out. If you actually try it yourself, you can actually come up and prove this formula here. I'm not going to do that because it's not required at this stage. So right now, this is just another cool new toolkit. We're just extending what we did in 2 dimensions to 3 dimensions. Other things are exactly the same, unit vectors. If you find the length of your vector and you say, okay, well, I just want to go 1 unit in that direction. So just take the vector and times it by 1 over the length of that vector. Now, and we'll go through algebra. There's a few kind of conventions that are not kind of permitted. One thing is try not to divide vectors by scalars, although it's you might see it in other books. It's not necessarily that important, but we only times by scalars. So if you want to divide, it's you times by a fraction, 1 over, if you want to do a division. Okay, another one I didn't underline, which I just added on. If I wanted to vector parallel to A with length of B, where B is a scalar in this case. Now, parallel could either go in the same direction, that would be the positive case, or in the opposite direction, which is sometimes referred to as anti-parallel. You won't see that in the book, but it's in other books. Anti-parallel would be the negative, so it actually goes in the opposite direction. You'd have B divided by the length of A times by A. So now it goes, if positive, in the same direction as A with length B, or opposite direction if negative with a length of B. All right, I'm assuming B is also B is greater than 0. All right. Other operations, these are very similar as well. We said we just extend them to 3 dimensions. If we have a negative vector, that's the same vector in the opposite direction. So it is just the minus of all the components. If we add vectors, we add their components, x, y, and z. If we subtract the components. And you notice we're not doing a lot of drawing here because, as we said, the drawing is helpful to a point. And oftentimes what we're going to do, unless we don't have to, we're going to draw things in 2-dimensional space unless we absolutely must draw it in 3-dimensional space, like we have a 3-dimensional object. And we spend a lot more time doing the algebra than doing the drawing. So yeah, we're just going to do the algebraic approach for these ones. So the operations are all algebraic. All right, so yeah, A1 take B1, A2 take B2, A3 take B3. Scalar multiplication, you're multiplying the vector with a scalar. You multiply all the components by that scalar. Okay, and just the last two ones that we're going to go through in the work we're going to see. Position vector of A, which means you start from the origin. So O is a coordinate point that's always 0, 0, 0. So if you go from O to A, then sometimes vector A is represented by the vector that goes from O to A. So thereby, I would say that that would be the vector A1, A2, A3 if position A is coordinates A1, A2, A3. Okay, and the last one, vector between points, A to B. That means you end up at B, so including B, and you have to remove the A. That's the way I like to think about it, but there's other approaches. And we'll see in some of the notes, another approach is to think about in terms of position vectors. So if you have, if you want to end up at B, so you get your position vector OB. But we need to go from A, so we need to go, okay, we'll go from A to O. If we go from A to O, and we add those, and I go from A to O to B, then I'll have AB. But then you have to think about, well, that's the, if you switch the direction of the letters, you go in the opposite direction, also known as a negative vector. So it's O minus OA plus OB. So you have the minus the position vector of A, that's why they're all negatives. That's how that works. All right. So at this point, I'm just going to go through random exercises and we'll look at the applications of some of these. So I'm just going to flip over a page and I'm just going to start selecting questions at random. I'm just going to do one or two from each of the sections. And then we'll see how we go these concepts. Okay. So having a look here. All right. So let's just go through the textbook and look at some of these applications. All right. So the magnitude, actually, there's your derivation right there. So you see they've actually they've worked out using right angle triangles on these planes. They've used a plane of XY to work out OB. And then they use the plane of, well, actually, this is entirely, you made a plane, a right angle triangle out of OB and the point P. And if that distance up is C, then, yep, see, OB squared plus C is A squared plus B squared plus C squared equals, okay, and there's your formula. So that's the proof there. All right. Two vectors are equal if they have the same magnitude and direction. All right, and that symbol means if and only if. So, yeah. If A and B are equal but do not coincide, that means they don't share a common point, then they are opposite sides of a parallelogram. So, like, you can always draw them parallel to each other, and then you can basically join the ends, and these ends will be equal distance. So the idea of parallelism as well is you have vectors that are equally distance apart, so it would form a parallelogram. All right. Okay. So maybe I'll take a couple of problems here. We'll just have a try a few of them. All right, so 5A. Okay. I'm not going to draw any vectors in space because I've done that before. I'm not going to bother with distance formula because I've done that. I'll just take, well, I think the question 3 is quite easy, but let's just look at the application of it. So if you've got an unknown, you could use this to work out an unknown point in space, for example, because you know where the other point is. Like, so you've gone from A to B and you know what B is, and you know the vector that moves you from that point. That can be used to find other points in space. All right. So if I do that, well then A minus 4 must equal 1, and then A equals 3. I must resolve the space we've got. 3B minus 3 equals 3, B equals 6. C plus 2 equals negative 4, C equals negative 6. There you go, now you know all those points. Okay, So what if we had something like unit vector of take 4b? Well, if I had that, then so if I have this vector, I'll call that, maybe I'll just call it b, this is question b. Okay, 2/3 minus 1/3. Well, and we know that length of b is 1, and thereby I could express it like this: k squared plus 2/3 squared minus 1/3 bracket. Now the square root is redundant because it's equal to 1. If we just square both sides, then I can get rid of the square root. But I thought I'd just put it there just for the full application. So k squared plus 4/9 plus 1/9 equals 1. All right, so 4/9 plus 1/9 is 5/9. 1 is 9/9. If I subtract that across, it would actually be 4/9 on the other side. And then you can take the square root. Now, k would have two answers, plus or minus 2/3. So there are two potentials to get a unit vector out of this. So k can be plus 2/3 or minus 2/3. Both are acceptable. Okay, so that was 5a. Easy peasy. Operations. So again, this is just extension from the two-dimensional stuff. So let's have a look at some questions from 5b. 5b. All right. These all look pretty easy. What should I do? Okay, maybe just pick some one of them. Okay, question 2. Okay, A take B. This is question 2H. A minus B. Okay, and so let's just go not always conventional, kind of put your vector inside there, that sort of bracket, but just to keep it consistent. Okay, so A minus B, so there'll be 1 plus 2, it'll be 0 minus 1, 3 take 1. Okay, to simplify that, 3 minus 1, 2, square root, 3 squared plus negative 1 squared plus 2 squared, 9 plus 1 plus that's square root 14 units. You get in the habit of just writing units for the in place of anything, any context in terms of the length. All right, find scalars. Yeah, similar to the other problem solving. Okay, let's do one at least. Question 4. I'll do B. Okay. Now, essentially, we can kind of add things, and you can do scalar multiplication on the fly in terms of that. So that's A, 2B, 0B, minus B, and C. So you can almost like just add these as you go. So if I just was to just, I'll write it out first for the purposes of the exercise. So we got 1, 0 plus B. 2, 0, 1 plus C 0, 1, 1. So this is just going to, it actually kind of feels like you've got linear operations, which I think is what we're going for here. If you actually did, if I did this in a, the first thing I would do if I was doing this in multiple steps, multiply A into those spots, B into those spots, C into those spots, add, and then add again. But because I just feel like taking shortcuts, I'm just going to go like this. Okay, I'm just doing component by component. A times 1, B times 2, C times 0. So it's A plus 2B equals minus 1. A plus no B plus C, so A plus C equals 3. You notice I'm leaving a gap here, and that's not important, but is habit forming when you start using kind of row operations and things of that nature, which is not going to come up until I think it's chapter 6. But you can see that sort of thing. So you can, okay. So yeah, okay, find scalars, and then basically you can break this up into all right, so A plus 2B equals minus 1. A plus C equals 3, and B plus C equals 3. So you can isolate one in terms of the other. So for example, if I was to isolate, which I think was the easiest way to go without actually doing an entirely different branch. Sorry, I didn't realize I was actually showing that. So there we go, just the camera, there we go. All right, wasn't even showing that off. All right, so we're at this stage. Without having to go into whole row operations here, you can essentially just go and isolate one variable in terms of another and substitute into one of the other equations. So if I was to say, okay, like C equals, we'll get rid of C. C equals 3 minus B. And then I could write the second equation in terms of A plus 3 minus B equals 3. So putting into here. And then maybe, so that's A. And bring that across. So that'll be A minus B equals 0. So we've got two equations then in terms of A and B. A plus 2B equals minus 1. And A minus B equals 0. Now I'm going to subtract this one from the top one. So then it's A take A is 0A. 2B minus B is 3B. And then 0 take 1 is 1. So B is a third. And then I can substitute into everything else. If B is a third, C is, well, actually, no, I'll just do A. From that equation, A is going to have to be 4/3. And is that consistent here? 4/3. No, I think I might have done something wrong. No, A has to be a third. That has to be 0. What am I doing? I don't think that's right either. What have I done? What have I done? So if I'm probably not doing this in some sort of Zoom thing, is no one can mention where I made a mistake. All right. So 3B, I think that was right. I subtracted those, unless I made a mistake earlier on. All right. No, that was meant to be minus 1. That's a mistake, because I was subtracting that. So then 0 is minus 1 takes 0. My bad. Minus, and then A is also minus. And that makes sense in terms of that one. It's good to check these things so you iron out mistakes. All right, so yeah, if I had A, which is minus 1, and then two lots of minus a third, minus a third, minus 2/3 is minus 1 whole. And then C equals 3 take B. C equals 3 minus 1 minus negative third. So that's 3 and a third, or 3 is 9, so then 10/3. Okay, that's that. I mean, the raw operations was the harder thing. Also, I'm not teaching the kind of formal way of doing that in a matrix form. So that was actually the hardest part, which is, yeah, what we're learning here is actually just the vector operations. Okay, I'm not going to do any more of those. All right, vector algebra. It's I find it funny when I'm teaching kind of algebra, and I think most of you think you know what algebra is. Um, you spend most of your primary school and high school education learning one form of algebra, which is the algebra of real numbers. So all your stuff about bed math, or you started off probably bod mass. First thing you did was you learned how to count. Okay, so you understand like the natural numbers. Then you knew how to add, and then subtract. Zero might have come into it somewhere. And then you might have learned fractions first. So you learned rationals, or at least your positive rationals. And then you start learning other operations. So you got your multiplication, division, and there's orders of sequences. That's where you had your bod mass, and you learn the exponents, and you got other special functions and things of that nature. Now that's just one form of algebra. In fact, those watching this in the year of 2000, you've actually learned a few other forms of algebra already. You've learned the algebra of complex numbers. There's a few things a bit different about those, but some things translate very well. And vector algebra, well, that's a different form of algebra as well. Now, most of the things here are going to translate pretty well from the algebra of real numbers, and some things later on that you add to this will not. So we use the idea something like 2 times 7 is the same as 7 times 2. They're both 14. Now, that's also true for some of the operations we do here, and we'll go through some of them. But for other ones we'll learn later on, in particular the scalar product, it doesn't matter the order, but the cross product does. And we're not learning that today, but we'll learn it later on. The cross product, if you change the direction, it does actually, if you change the sequence and how you multiply them, it does change the outcome. And there's other forms of algebra, matrix algebra. Yes, that's also true. Matrix A times matrix B is not the same as matrix B times matrix A. In a lot of cases, you can't actually, if you can complete one, you can't complete the other, unless there's certain conditions. So the vector algebra, so let's maybe put this out. We'll just call this is 5C now. All right, these all have full names. So the idea that if the sequence of addition doesn't matter, it's called the commutative property. All right. And if you extend that over, so the idea that A plus B then plus C is the same as A plus B, A plus, and then doing the B plus C first, that's the associative property. And we kind of know this because the idea, if you take vector A, you draw vector A out, you go to B, and then you go to C, and you join that up. Well, if you started from any of those points, it would look a bit different, the path, but you end up, from where you started, you end up where you ended. So these are true. Now, there is an additive identity. We call that the zero vector. See, it's in bold and it's tall. So that's 0. So that is the zero vector. The zero vector is, funny enough, 0, 0, 0 in 3 dimensions. Okay. There is an additive inverse, which is the negative vector. Yeah, if you have the inverse of addition, and you end up with 0 in that. Okay. Scale multiplication has what we call the distributive property, which is you've seen this in real numbers. So if you had this is how you're able to take out factors. So like, okay, that x 2x squared plus 4x, you can take out a factor of 2x, for example, and that was the distributive property because it multiplies the inner. All right. Okay, this one is would just be for this form of algebra. So this one's a bit different. Okay, so but actually, I think we saw something similar in well, actually, no, we did in specialist maths because this is actually a property of vectors, and we use an analogous relationship with complex numbers rather. In complex numbers, yes, you could talk about complex number z and the modulus of z, which is also the length. can be expressed this way as well. This is also true. So this is not surprising we've seen this again in vectors in 3 dimensions, because it's true for complex numbers, which are a type of vectors in 2 dimensions with some other properties like the square root of -1. Okay. Now this is just a notation thing. If you wrote it this way, I wouldn't take any marks off in a test, but the convention is that we have a scalar multiplication. We don't actually have a scalar division, although it's kind of like, well, dividing by reciprocal, times it by reciprocal is the same as dividing by the number. So I really don't see why this is a thing, but I think they're teaching you habit forming, that not all rules for one form of algebra apply to others. So that's where they're going with that. All right. So now we can do a little bit, there's more kind of a little bit problem solving. So let's say, for example, take something like question, all right, I'll take question 3. Let's just go for the gusto. And I'll take B. All right. Well, if I've got a statement like 3 vector x minus a equals 2b, well, let's just do what we would do. We would add a to both sides. So that's the idea that, okay, there is an inverse. The inverse of minus a is plus a, because it's the inverse of minus a would be minus a by what we just learned. It seems trivial, but because it is, because it's that similar to stuff we've already done before. So we just bring it across, and you'd be doing that with non-vectors, like you just, if we taught the vector notation, 3x minus a equals 2b, you know what to do. Okay, except for one case, if we're going to keep it a bit more precise, we're going to times by a third. So it's 1/3 a, and that would be 2/3 of b. So add those vectors. Okay, let's now put it into context by putting what those vectors are. So we've got 1/3 of -1, 2, 3, plus 2/3 of 2 minus 2, 1. Okay, there we go. Equals, all right, I'm just going to again just do the shorthand. That was -1, was it? Yes, -1. Minus a third, 4/3 is 3/3 is 1. Okay, 2/3 minus 4/3 is minus 2/3. And 1/3 of 3 is 3. 3 plus 2/3, sorry, 1 plus 2/3, 1 whole plus 2/3 is 5/3. Okay, and there we go. So just rearrange first, substitute, solve, easy. Moving on. Vectors between 2 points. So this is where we start moving into kind of real coordinate geometry. So a vector, like a little a vector, you could place that anywhere in space. It's a movement. It's not joining necessarily 2 points. But if you have a vector with 2 capital letters, that does mean I'm going from position A to position B. Now you can have a vector that's equal to it, but that vector doesn't necessarily have to share the points of A and B. So if you've got something like a parallelogram, then you could have vectors which are equal as vectors, but they don't share the same coordinate points. That's fine. You don't need the vectors don't have to have the same coordinate points if they're parallel. If they're collinear, they do on the same line. So yeah, we went through this already, but that's all right. So let's go some of the problem solving exercises maybe. I think we know how to do this. Position vectors. Yeah, okay. All right. All right, so I want to try this question 6. The rest of this seems pretty straightforward. All right. The shortest distance of Q to the y-axis so if maybe kind of draw like, okay, we've got, maybe just draw a little bit of space here. And I'm just going to guess where the position is. I'm not going to draw it up to some sort of scale. But instead we've got our X, Y, and Z as there. I'm not sure if that's how I did it before. Nope. There's not necessarily convention to this either. You can see some drawings where the axes are skewed more, like these are more like spaced out like 120 degrees instead of like being at right angles. But this is a common format, so I'm going to stick with it for now. All right. So roughly, if I decided that I was going to, all right, question 6. So Q, we've gone 3 in the X, 1 in the Y, and -2 in the Z. So actually down here somewhere. So if I do, okay, like 3, 3, 1, and then down 2. So that's kind of like, there's your rectangular prism that makes that up. That's very poorly drawn, but it's just a little sketch. Okay, so the y-axis is here. Okay, so the shortest distance is always a straight line. So if you think of it this way, okay, shortest distance to the y-axis, well, that's that. Okay, so that's a coordinate point of 3, 1, -2. All right, so I've drawn this kind of conceptually. Now I can't measure these, like I said before. I can't just go and measure it. I can't draw a scale diagram and make this happen. All right, but what's special about the y-axis? Well, it's where z and x would equal 0. So z and x equals 0. Then this point here is 0, 1, 0, because we've kept our point in the y. Now you could go and work this all out like a good all right, well, it's just Pythagoras, isn't it? Yeah, it's yeah, pretty much. You could go just conceptually look at that and say, well, I've moved -2 in the z, and I've moved 3 in the x. So thereby, it is the answer for part A is -2 squared plus 3 squared, which is 4 plus 9 is 13. Yeah. Oh, hang on. No, it's 3, 4, 5. Yeah, units. That's part A. But then again, if you consider this, and you can, okay, well, these coordinate points, I can work out the distance between points using the formula, but it's yeah, you can just go back to 2 dimensions because you've only moved in 2 dimensions. I think that's easier that way. All right. So what about the origin? Well, the origin is, if I take it from the origin to that point, then what was the point called? OQ is the vector 3, 1, -2, and its length is 3 squared plus 1 squared minus 2, sorry, plus minus 2 squared. All right, so 9 plus 1 plus 4 is root 14. Okay, sorry, didn't quite see that, did you? Okay, yeah, so that's B. All right, now the XZ plane. Well, the XZ plane, Now, I'll give you a little hint here. The xz plane is a plane for which all points have an x. Sorry, the question was actually the yz plane. My bad. The yz plane. So like there's this surface here. Okay. Rub that out. YZ plane. Okay, and that's the coordinate with the x coordinate equals 0. All right. I think that's literally just 3. Because if you move, so this point here before you move the 3, that has a coordinate of 0, 1, minus 2. So it's 1 in the y and minus 2 in the z. That's part of this plane. So I know I kind of draw it like it's in this quadrant. If that was a quadrant, it's not a quadrant because it's not. It's three-dimensional space. I make a habit of it, just writing, that's just drawing, like talking about the plane in the positive part. But the plane's also down here. Yeah, so this comes out a perpendicular out 3 units in the x. So this one is by definition 3 units. Another way to think about it is, okay, well, no, I would have to. There is other ways to do shortest distance from a point to a plane, but that's we need some more advanced concepts for that. We need the scalar product. We're not ready for that yet. So conceptually, I hope you kind of get the idea that okay, well, you only need x to be 0. So if the other values had no change, there'll be no length. If you have any movement in any vector direction, any component direction, it would increase the length somewhat. So like if you have, okay, if you kept these as 1 and minus 2, where this is 1 and minus 2 as well, then you've only moved 3 in the x. That's the shortest you can get. Anything that's not a straight line is, yeah, it's going to be longer. So the shortest distance is a straight line. So straight line from this plane. So if you draw a plane and you just have a vector that comes out at right angles, and that's a precursor to some of the stuff we're going to be talking about later on. That's the shortest way to get from a plane is to launch straight out of it at right angles. Okay, and that's what we've done there. So that's just 3 units. And I've lost that. 3, yeah, that's 3 units because you move 3 units. If you just pick the point where you haven't moved anywhere in the y and the z, you only move 3 units in the x. So it's 3 units of length. All right, so that is 3D. Anything else that's special? All right. All right, maybe I'll take something else on that. All right, maybe we'll take something like 12. Sorry, that'd be interesting. All right, so watching my screen now. All right, question 12. All right, consider, we've got 3 points in space. All right, find the position vector A to B, hence the length of A to B, A to C, C to B. All right. All right, sounds like a bit of a grind, but let's just do it anyway. Skip ahead if you don't want to. If you just want to try for yourself. All right, so A to B. In a shortcut way, instead of having to do the subtraction, I just kind of think about it in terms of the number line. So I'm going from A, I end up at B. I go from minus 1 to 2, 2 to 0, 5 to 3. What motions do I have to do to get from A to B? Well, I have to go 3 positive units, minus 2 negative units, and minus 2 in the Z as well. All right, that's the shortcut form. I'm just going to get all the position vectors first. So that's A, B, and C. I'll just do the distances in a minute. Okay, AC. All right, so I go from -1, so AC. -1 to -3 is -2. 2 to 1 is -1, and 5 to 0 is -5. BC. Sorry, CB. Direction matters. Nah, rub it out. CB. So careful the direction you're going. So I'm going from C to B. So -3 to 2 is 5. 1 to 0 is -1. And 0 to 3 is 3. Okay. Length. All right. 9, 4, 4. So you can just square these ones. So take away the negatives, square them, add them up. So 9 plus 4 plus 4. If you're just doing shorthand, 13, 14, 15, 16, 17, root 17. Okay. 4 plus 1 plus 25, that's 30. I suggest don't simplify that one. Actually can't. There's no square numbers. 30, yeah, you can't take 4 out of that. But all the same, if you could, don't, because it would be easy to spot the Pythagorean relationship if that's what it is. But we'll have a look otherwise. If it's not Pythagorean, like it's not a squared plus b squared equals c squared, then it could be collinear, which is a trick when the triangle collapses into a line. It's definitely not equilateral. Could be isosceles. That would have to be one that has to be equal. Let's have a look at this one though. C to B. All right, so we got 25 plus 1 plus 9. All right, that's 35. Let's classify the triangle ABC. Oh boy. Five, okay. Let me just double check I've got these ones right. Okay. A to B, 3, -2, -2. AC, -2, -1, -5. All right. And CB, 5, -1, and 3. Okay. So it doesn't seem, or you can rule out isosceles straight away just by looking at that. You can rule out, I don't think it's Pythagoras because, okay, 17 plus 30 does not equal 35. I'm assuming it's meant to be a special triangle, but I don't. Okay, so if you think about it, okay, well, Pythagoras, like right-angled. Ace. Isosceles. A equals B does not equal C. Equilateral. A equals B equals C. I mean, you can also say, yeah, you can have an isosceles which is also equilateral. Then, if it's isosceles and not equilateral, then it can't be the third length. It can't be the same. It's also not collinear, which would be like collinear is not actually a triangle. It's a triangle that's collapsed into a straight line, which would be A plus B equals C. That's the end of your triangle quality. This is just a boring scaling triangle. Look at it. Unless I made a mistake, I can't see what my mistake is. Just square them all right. 4, 3, 2, 4. Did I add them up right? 8, 17, 30, 35. It's just a boring or scaling. Scaling is kind of like all of the above. So what were we doing? Doing 5D question 12. Oopsies, too far. 17, yeah. Yeah, it's this boring scaling triangle. Oh, yeah, so we're right. Except I can't spell scaling. E, 2 E's, no I. Yeah, scaling is just like any triangle that's not special. So our triangle wasn't special. Sorry. Now I was right. It was just boring. All right. It doesn't. Yeah. Well, at least there's a way we can summarize all the special triangles here. Right-angled, fits Pythagoras, isosceles, ISOSCELES. Two lengths are equal. Third one's not. If it's not equilateral, then there's all three are equal and collinear. You could have an isosceles that's also right-angled, and there's like two of them are two sides are equal, and the squares of those two sides is equal to the sum of the third square. The sum of the squares of those equal sides are equal. I just say it again. You can have an isosceles right-angled triangle where the two sides are equal, and the sums of their squares is equal to the square of the other side. So that's both of these statements. However, yeah, we just have a boring triangle. So let's just go back to our boring question. All right, where were we? All right. Alrighty then. Okay. No, I'm disappointed in new triangles. Okay. Yeah. And these parallelogram stuff, particularly this third side stuff, is stuff you've done in two-dimensional space as well. You just because we could always draw parallelograms in a plane. So you've already done things like this as well. But the idea is, okay, well, you can work out C by adding the vector between the points of A, B onto D. So, for example, if I just wrote this as a general example, you can solve all of these ones. If C was unknown, so C is kind of like OC is not known, but if DC equals AB, then OC can be written as OD plus AB. So just basically, if I just went and worked that out, okay, so it's like O to A is 3 minus 2 minus 2. So I could just do that. I could just add that. So it's 6, 1, and 2, just in my head. Okay. You can actually work out the point of C. So yeah, that's what I just got there. Yeah, I just guessed it from well, I didn't guess it. I just carried numbers in my head. Yeah. One thing I didn't actually cover was midpoint, but I think midpoints of points. You're just taking each component, adding them up, and dividing by 2. And so you also do it for the x and the y, and now we do it for the z as well. All right. So yeah, I don't think that's too there. So we've actually proved it's a parallelogram. Okay. Yeah, I don't find this stuff particularly challenging, so I think I might vector methods of remaining vertex. Yeah, so I've talked about this in general as how you approach finding the missing vertex of a parallelogram. Okay. Maybe something like 21 might be interesting. Let's have a look at that. Let's do 21. And this, I think this will be the last question I do from D. Okay, in the given, so we don't have a parallelogram. We have a, I think it's not a rhombus. It's a trapezoid because they're parallel, but they're different lengths. In the same BD is parallel to OA in half its. So BD equals 1/2 OA. And OA is represented by vector A, so BD equals 1/2 A. Okay, actually, I've actually answered the very first part of that, part A. I was just writing that down from the information they gave in the sentence here. Okay, so AB. Okay, I can go from A to B by going from A to O. Just take a different path that you know. A to O, and then from O to B. Oh, well, we kind of, I suppose is that really surprising? So it's basically B take A, because that's in the opposite direction, because you swap the points. So you subtract A. And in BA, well, if we swap the points, then it's A take B. That's not hard. Because if you think of it this way, you can follow this around the drawing. B to A minus B plus A. Yep. Okay, yeah, let's move on to something more interesting. So we've done B and C. Okay, maybe let's go over here. Let's do D. D. All right, D. O to D. O to D could be represented by. Now you can go. We don't have A to D yet. That's the next question. So we have to go OB then BD. Which we already know what that is. OB is B, and BD is 1/2 A. So there you go. Here's B plus 1/2 A. Question E, A to D. A to D could be done by going from A to O plus O to B. Oh, basically from O to D, we can take a shortcut because we got that in the previous part. So that is equal to minus A, was A to O, not O to A, plus B plus 1/2 A. So that would actually be B minus 1/2 A. Whoops. There we go. AD. Oh, DA is just the reverse. One half A minus B. Easy peasy. Yes, I think so. Parallelism. Okay. So this is the last one we're going to be covering. Yeah, you can draw many vectors that are parallel. They point in the same direction, have different lengths. And okay. If A is parallel to B, then there exists a scalar K, such as A equals KB, and if A equals KB for some scalar K, then A is parallel to B, and parallel can also mean anti-parallel as well, so it can be in the opposite direction. Just be a reminder, so K can be negative, but this expression would always be true. Okay. Yeah, it's simple enough. Okay, so to remind you of this, so just the key terms. Unit vector is the length of 1. The unit vector v is 1 over the length of v times v. A vector b of length k has the same direction a. So so b equals k over length of a times scalar multiplication with the vector a. So that's how you can, so basically, it's like a unit vector times by the length of k, that's b. All right, a vector B of length k which is parallel, so rather than pay attention, to A could be B plus or minus k on A. So that also takes the connotation that it could be anti-parallel, so in the opposite direction. If it's the same direction, k would have to be positive in that case. I don't supposed to say that if it's the same direction. Yeah, in this case, k could be k is positive here, but you can also take the fact that you have a plus or a minus, so thereby it can be opposite direction. Yeah, that is supposed to say it, but yeah, in this instance, k would have to be greater than 0. I think I wrote that in my notes to start off with. Again, this is opposite. Yeah, collinear points, another one to add to the list of things. A, B, and C are collinear if they're parallel and they share a point. These ones are parallel and they share the point of B. They're there. All right, so again, let's go through some ones. Find R and S. I can see basically just by looking at the numbers for 1A, for example, A is equal to, B is equal to minus 3 times A. So thereby minus 3 times A, R is 4, S is negative 9. Not special. Okay. What can we do? So following RS is in the same direction as PQ and 4 times the length. CD is 2/3 the length of AB and is in the opposite direction. And these are collinear. I think we eventually will come to ratios of division. I think that would divide ln 3 times lm, so thereby n lies on the ratio of like 1 to 2, with the total length being there. So you'd have, like, if you had a vector, you have L, then you have N, then double that length again, you've got M. I'm sure we'll come to problems like that in a minute. But these are collinear because they share the point of L. Right, direction vectors, PQ, precision vectors rather. Okay. All right, maybe I'll take something like these are mostly operational ones. So yeah, just you follow the formulas. I'll take something like question 8. So now we've got 5e. Okay, I'll do some other ones as well, but later on. Okay, let's just do a proof of something that's collinear. I tend to work in the direction at least in one way. So I might if I went in order of x, I'll go from R to P to Q, because that seems to be an increase in x in that direction. So let's look at RP. If we go from R to P, so we go from -1 to 2, which is 3. We go from 7 to 1, which is -6. And we go from 4 to 1, which is -3. Okay, now let's go from P to Q. P to Q equals, all right, so we got 2 to 5 is 3. 1 to -5 is -6. Okay, that's -3. All right, well, look at that. It's not just, that's just a happy coincidence as well that RP equals PQ. It has a scalar multiplication of 1. That just happens to be coincidence. You could also say that in that case, because we went from R to P and P to Q, and thereby P is basically the midpoint because you travel the same distance. Yeah, I mean, because they have the same numbers, you got the same distance. So you could also say, that so that implies that these are collinear points. And you got the bonus fact that P is the midpoint of RQ. Okay. And maybe I'll do one more. I'll do, okay. So we don't have a ratio division. So maybe I'll just go back and I'll deduce all right. No, these are all kind of operational questions. Let's just do one more. Let's do D. Okay. So for D, I like to go in the order of something that's increasing. So you see, the only one we have to work with really is Y, because these are unknown. All right. So if I go from L to K and then from K to M, because I'm going from and I've got an increasing Y value that way. All right. So LK. Okay, L to K is -3, and I've got -3. I got okay, -3 to -1 is +2, and -7. All right, then all right. Next one would be L to M. Hang on. No, I want to go from K to M. Okay. All right, K to M. Well, -1 and add A, so A -1. I go from K to 3. And I go from 0 to B, which is B. Okay. Now, the thing about that is we need to find an expression that goes something like this. And the reason why I kind of focus on the y coordinate is because I can do that with the y coordinate. So these have to be consistent. So so basically I can just say from that equation, 2 equals, actually maybe I'll put the k over here. Okay, 2k equals 3. K equals 3 on 2. Because then I can just apply the k over here, and at least it's kind of dealt with on that side. I don't have to keep moving it back across, so I'll put the k on that side. All right, so long as there's a scalar value times by this vector equals that vector, then that's true because they share the point k, so they're collinear points. So 3 on 2, so thereby I can do the rest of this. Let's look at the x. The x coordinate says this. No, I'll make it a capital X. The x component says, okay, well, that would be -9 on 2 equals a minus 1. All right, so if I add 1, a can be written as, well, 1 whole is 2 halves, so yeah, it's got -7 on 2, and then I don't think you can see that. My bad. Let's move that over. There we go. And then finally, the z coordinate says the following: 3 times 7. Yes, it is. Okay. Minus is what it is. -21 on 2 equals B. Straight up. Got it. That's all you had to do. All right, that's it. So that's a fair bit of work, but it's all stuff you've seen before, and it's yeah. I'm not going to do the scalar product because there's a few things we're going to add to the scalar product. When it comes to, because its relationship to right angles in space. So I'm not going to go into 5F in this video, but I will do another video shortly. Okay, So this one's long enough, so let's leave it here. All right. Good luck.